So first, an announcement about. Is this working? Yeah. First, an announcement about next week. We're going to have one Maldacena, and we're combining it with our regular weekly seminar. So we need a slightly bigger room. It'll be in Austin, in that next building over there. There was nothing in here. Austin 101, and there's a related assignment on the web. Okay, so it's a great pleasure today to have as our special guest lecturer my longtime friend, colleague, and one of the world's greatest mathematicians, Shing-Tung Yao, give a lecture today. He's known, well, the things that physicists know about him is only a tip of the iceberg of his deep work in mathematics, proving the Calabi conjecture, and more generally, and proving the positive mass theorem. And more generally, I think he is rightly credited with sort of bringing the theory of general relativity to a kind of new level of mathematical sophistication and rigor. And it's something he started many decades ago, and it's now a major field in math departments around the world. And so today we're going to hear some of that, about some of that.
Okay, thanks. It's been a long time since I know Andy first time in Princeton 40 years ago. So it's a great pleasure to give a talk here. So I will use a little bit on this PowerPoint, but later I will write on the blackboard also. So some of these papers were with my former student, Muda Wang in Columbia, but not all of them are on those papers. So in general relativity, as we know, you must learn already clearly that we have the action, which is taking variation of integral or the scalar curvature of the space-time. It's always 3 plus 1 in my formulation. In my signature, because I'm a Riemannian geometer, use plus and minus, while most physicists use the opposite. But it's a question of convention, of course.
No, we're using minus plus.
Oh, yeah? Okay, good. And then plus the matter density, as you know. The matter actually is quite interesting. It can give some interesting phenomena that is unexpected when you put gravity away, put either one away, but only couple together give some interesting phenomena, mathematically at least. So we know, of course, this at the beginning it's a little bit survey, you know them all. Oh, by the way, but in any case, I should emphasize, many people kind of ignore the major contribution by Minkowski, who was actually a teacher of Einstein. And the more I look at it, the more I think this, at the beginning when I learned general relativity, I think this is rather trivial business to write down this. But it's really Minkowski who really knows that special relativity is beautifully, geometrically encoding everything in this space-time. I think only after that, Einstein knows that GR is going to be governed by tensor instead of by scalar. Newtonian gravity is a scalar potential. But only after this, we know it should be a tensor, okay? Because the metric tensor has to come in. I think this is one of the very major breakthroughs in 1908, which many people did not seem to think so, at least in the literature. Well, so we all know this famous Einstein equation. The left-hand side comes from integral R, the right-hand side comes from integral L. And in classical relativity, we always assume that it satisfies some kind of condition. Namely, the Tij has to satisfy the weak energy condition. If we don't make this assumption, there's nothing to talk about because we have to make some assumption on matter or on something in order to start with. So we always make this assumption. But of course, I understand quantum gravity may want to violate it a little bit, but many of the methods that we are discussing allow you to violate a little bit, but how much you can violate is a question. And that's interesting to know. And of course, the first thing important solution of Einstein equation was force field. Actually, I'm always very found it funny when Einstein and Grossman make the mistake on writing down the first Einstein equation. The first equation they write down is vacuum, no matter. That case, the equation is correct, and I don't know why Einstein did not derive this solution in 1912. He could have potentially derived this equation in 1912, but he did not do it. If he did it, he would have derived many things. But instead, he wanted to approximate the solution, and that leads to nowhere as a result, and then he wanted to change the whole thing. So I found it historically quite rather interesting, but I could not read German. I don't know whether how Einstein derived his solution. He solved the equation approximately as a physicist, and that was a big mistake. He didn't think more mathematically. He did not want to solve the equation.
Didn't he have the wrong equation in there?
No. For vacuum, it's the same equation. For vacuum, this vacuum, remember. If you take L equals 0, he should have derived this solution, but he did not. That because he lost confidence about solving the whole system directly, he wanted to approximate it as like a physicist would do, and that was a big mistake. That's why it delayed 3 more years for him to find the solution. So I don't know why he didn't try to do it. It's exactly the same solution. It's missing the R term, remember, RIT minus. When it's vacuum, R equals 0. So there's no difference. Anyway, this is, of course, one of the most spectacular solutions to a nonlinear equation is due to Kerr. And the Kerr solution is now used by everybody, as we know. Now, why I write down all these things at the very beginning? Because it tells you what kind of behavior we should expect near infinity and order. And these, of course, were axisymmetric solution for the Einstein equation when you have a circle action. And for the previous one, is spherical symmetric. It's much easier to write down. Almost everybody knows how to derive it in a matter of few years. But this takes long time. I mean, basically, 50 years after this. It shows how difficult to solve the Einstein equation is. And of course, the major problem in GR, classical GR, or quantum gravity, we don't know how to solve the two-body problem up to now. And everything that we talk about two-body problem is just a matter of guess. And we don't know what the results are supposed to be when two bodies are interacting. If the two bodies are very far apart, we can believe by gluing together it looks good. But when two bodies are very close to each other, it becomes strong interaction. Many results based on post-Newtonian calculation is difficult to believe because they don't work in that way. I don't believe that, but we are using it in any case. So I suspect many results are not quite what physicists said.
But now we're comparing theory and experiment.
Well, that's why I don't believe that experiment, which you don't. Because there's nowhere to check that experiment is correct. The two bodies strongly interacting, you get some results, and the numerical calculation, which we know nothing whether it's right or wrong. There's nowhere to check it. In one body problem we can check it, after all. We know something. Let me repeat again. There's virtually no rigorous theory or rigorous results saying how things should work when two bodies interact in a strong manner. When two bodies are very close interacting in a strong way. I do not know any single result which talks about them. Anyway, well, already in the Kerr solution, there's a very interesting phenomena. There's a now hypersurface there, which is the event horizon of the black hole. So this is the space-time boundary of the black hole where any event occurring inside cannot be detected by outside observer, as we all know. Now, of course, event horizon is a very difficult subject, although people in physics always talk about event horizon, assuming it's clear. But event horizon is assuming you know everything in the future. And in fact, we know nothing about the future. But we pretend we know it, and we discuss about it all the time. But anyway, in the case of Kerr event horizon is same as something called apparent horizon, which I will discuss a little bit later. Okay, if it's apparent horizon, we are much more comfortable because we know how to define it locally and all that, but not event horizon. Now, I want to point out the point is that in this space-time, we have, of course, this nice Killing weather field, which is the time we saw at infinity, and you preserve the metric, and that's good. But it has an important property that is non-standard. Namely, it is only timeline in this region. And there's no more timeline in the, it becomes space-like in this other region. So this creates a lot of funny and interesting phenomena inside this region, which we call ergosphere. Okay, so this is a region outside the event horizon, so you're supposed to be able to see it, and except at theta equals 0 and pi where they intersect. So this is a very interesting region, and this region has the following property which we should know. Suppose I consider dynamics of scalar field with the background being Kerr spacetime. So its propagation is described by scalar wave equation. So I fix the background, I look at the wave equation of the scalar field. So you look at the Lagrangian. Now the spacetime has a Killing weather field, and this defines a local energy density to you because there's a symmetry, continuous symmetry. Given continuous symmetry, you have a Lagrangian. From there, you derive a energy density. And it has the following form, which you can calculate by a standard way. Noether, the M in Noether's current, you can calculate it, and you come up with this density. Okay? So this takes a little bit of work to do, but I think any people who work in mechanics knows how to do it. From the Lagrangian, you derive the thing. Now this, well, anyway, this is due to Noether. By the way, Noether was in Göttingen at the time when Hilbert was in Göttingen, and it was a time when Einstein really wants to know how to derive his equation. According to Hilbert, in his paper, he said Emmy Noether should have been a co-author with him on that famous paper. And I believe Noether has major contribution to Hilbert to derive the Hilbert action. Einstein never thought about the action, only Hilbert did. But Hilbert said that Emmy Noether should have been credited for that. And the paper appeared only a couple of years later, Emmy Noether's famous paper on deriving current by symmetry. But anyway, so
She should have been on the paper with Hilbert.
yeah, that's what Hilbert said.
Then why didn't he put it on?
I don't know. I have no idea. Hilbert himself wrote in that way. But in those days, Noether is only I don't think she's even a graduate student. She's probably just assistant or something. In those cases, unfortunately, women are not considered to be that important. I think probably something to do with that. You know, both Hilbert and Poincaré tried to push Noether to be an important position, and they failed. Okay. But anyway, why I want to point out this is because the density, in fact, is negative somewhere. It's only positive if it outside the ergosphere. So this shows that density, energy density, could be negative, even for this case also. So positivity energy density is not that trivial. Just this example shows. So now, well, I don't want to go into much detail here. This for some other talk. So the higher order in the stability of the Kerr metric actually has been a rather important question. The linear stability, even for the Kerr solution, and this has been a problem for a long time. I think only recently, Darfermos and several other people claimed they could do it, but I think, as far as I can tell, they assume angular momentum to be small, and I'm not 100% sure the proof is complete, actually. But so you see, even until 1998, Novikov and Forov has also said that it's one of the few truly outstanding problems that remain in the field of black hole under gravitational wave perturbation. So linear stability of Kerr metric is actually a rather non-trivial statement, even up to now. after 60 or 70 years. Well, actually, after Kerr is 1960, so about 50 years, 60 years. Okay. Now, so this is a situation of black hole and all that. I did something with my friends, and we do some more calculation and study the Dirac equation, how things decay. But that's not my focus today. Now, so the point there is that the ergosphere has many strange properties, including energy extraction process proposed by panels and many other things. And one needs to understand that negativity of energy density causes a lot of trouble. And we need to handle that very carefully. Now, the problem comes from the fact that the gravitational field itself must have energy. After all, the potential energy of a pair of gravitating particles depends on their separating distance, and so depends on the gravitational field configuration. Now let me start to write something on the blackboard instead now. So we are talking about a 3,1 space-time, and 3,1 space-time, the infinity is difficult to say, although there's a Penrose diagram which proposes that it looks like this. But that's only assumption that you can write the space-time in that way. I mean, Penrose wishful, well, at least, but it gives an initial point to discuss about space-time and infinity. But this, in a way, is just assumption that you have a Penrose diagram. Penrose has been extremely anxious about knowing what the space-time and infinity looks like. I don't think he thinks this one is accurate. So there still needs a lot to be said whether Penrose diagram is correct or not. Okay, so that's partially because the space-time metric is Lorentzian, and it's very tricky to deal with Lorentzian metric. Well, so on the other hand, there are many formulations of space-time. The one that I feel more secure from point of view of mathematics is the initial formulation. This sometimes people call it ADM formulation. So ADM is three guys: Arnold, Desher was here in Brendas, and Misner. Okay, is Desher still alive? Somehow I thought he died, but no, still alive. Okay. So we take a slice, spatial slice, that will be called M, 3 dimension in N3,1. So I take a slice of space-time, and for simplicity, we assume this is non-singular. Non-singular, so the induced metric on it is positive definitely. So the metric on here is positive definite metric, space-like. Okay, so that's one thing. Now, besides metric, there's another thing. So this gives rise to the Gij that you know. But then there's also a way that the surface sitting in the free space-time. So this is the second fundamental form. So roughly, it's dij over dt. After you mod out the diffeomorphism group, this becomes a second fundamental form. Okay, Kij, I write it to be. Okay, this is second fundamental form. So this is after you mod out the diffeomorphism group ambiguity. So there are two parts that are sitting here. Two quantities, Gij and Kij. That governs how M3 is sitting in this space-time infinitesimally. So one is the induced metric, Gij. One is Kij, which is roughly is dGij over dt. Why do we want that? Because the Einstein equation is a second-order wave equation in a suitable coordinate system. So Einstein equation in a normal coordinate system can be written as dt squared over Laplacian Gij plus lower order term. Okay? So it's a wave equation in a suitable wave coordinate. So this wave equation, you talk about initial data, propagation of wave according to wave equation, these two data. One is Gij, one is the speed, the velocity. Okay. So in order to understand the Einstein equation, which in suitable coordinate has this form, we need to describe the behavior of Gij and Kij in time t. Okay. So in order to understand Einstein equation or the n3, 1, we try to understand the dynamics of this pair. So initially, when t goes 0, you are given some data, and they want to see what happens when t goes to infinity. Okay, so that's called initial data formulation. So before I go into dynamics or anything, the first question is, if we just study it, it's kind of difficult because well, the equation, Einstein equation, already tells you the equations for dGij over dt, dKij over dt. You can write it down as a system. dGij over dt will involve Kij, and then with some gauge group, how you do it. And this dGij will involve Ricci curvature and all that, and also involve the gauge group. Okay, that's how the Einstein would behave. You can look it up in any book. So the Einstein equation becomes a dynamical equation on a pair, Gij and Kij. Okay, it flows in the following way. The right hand side depends on Kij. The Kij depends on Ricci curvature of Gij. Okay, that's Einstein equation. Okay, that's called ADM formulation. Okay, but then of course a very tricky part is how to choose time, how to choose gauge, spatial coordinate, and all that. This becomes much more tricky than it looks. We have to deal with that. But before we do that, Einstein actually thought that in 1915 or 1918, he thought that now everything is done. You can write down everything. It's according to his own paper. Once you have the equation, you can derive everything. But this is far away from being true because there's two things. One is boundary condition. One is initial condition. So given a system like this, you have to deal with two problems. One is the boundary condition. When you're given an equation to you, if you don't know the boundary, you don't know what to do. If you don't know the initial condition, you don't know how to start. So this, for say, given a galaxy for you, you want to know the dynamics of it. You have to know what the initial condition is and what the boundary condition is. Both of them you have to know, otherwise you cannot solve it.
Boundary condition where? The boundary of the...
Well, boundary of the, how to cut the boundary. I mean, say you have a bunch of galaxies here, or two black holes in the set. Where can you cut? This is basically we are looking at infinite space. Okay, so that's infinite space. If you don't know the boundary, the equation will come up to be funny. So the question boundary condition is actually put in this way is asymptotic behavior of G and K. Okay, this asymptotic behavior of G and K. So now we are working on something which is isolated from you, from far away. Say galaxy, we are watching some galaxy far away from us. So we know that this will be asymptotic flat. Okay? Because the gravity is measured by the curvature and all that. So we are far away, so we should be close to 0. Okay? When we look at this whole thing. Now there's a major problem about what close to 0 mean. And right now, what this close to 0 mean is just because we come up with some condition which technically important and we just define it so that it works. So, for example, we want several quantities to be workable. One is total mass, what total energy you will call it, or angular momentum, etc. Okay, all the classical quantities that you know, like total mass and total angular momentum, we like to be able to define it. Okay, so in order to define it, we need something to go down to zero in a suitable way. Okay, so at the beginning, you just write it down ad hocly, see what you can do. And normally, I guess Einstein did it himself already. So Gij, we want to write it out to be like delta Ij, because it looks like Euclidean space outside a big bound set out near infinity, so delta Ij. And then we want to write it to big O 1 over R. Okay, so that it decays like 1 over R. Why 1 over R? The reason is that when we try to define mass, this term comes in to give the mass term. And then there's a Kij term. Well, besides total mass, there's a linear momentum. Okay. The mass is defined from this term. We don't need Kij to help. But Kij helps you to define the linear momentum. Okay? So in order to it to be compatible and finite, basically just I want to make sure this one is finite in the first place. So I just ad hocly put down this condition, but 1 over R and 1 over R squared. Okay? So now, of course, there are people trying to improve this bound a little bit better. Basically, it has to go to 1 over square root of R at worst. If it's worse than 1 over square root of R, so sometimes people put down 1 beta here. Beta is strictly bigger than half. If it's equal to half or less than half, everything that you see is complicated and no more true, simple. And sometimes people put down 1 plus gamma here, and basically gamma plus beta, I think, is bigger than equal to 2 or something like that. I forgot exactly. Okay, but in the old days, people just put R squared here. Okay, right out. Now, why I say that this ad hoc? Because it's not clear that we could not allow the decay to be asymptotic flat to be much slower than what we have been using. And there are some space-time like Chalman space-time decay also asymptotic flat, but doesn't decay that far. So we have to be kind of open-minded to allow this decay to be better than what we have been using. The reason we use it is simply because we want to make the total mass to be well-defined and the total linear momentum to be well-defined. And then when you come to angular momentum, you need more. Because you see, angular momentum has some linear term. If you are not asymptotic fast enough to delta Ij, they may not cancel. And in that case, you will lead to disaster. It's no more finite, the angular momentum. So all these standard quantities that we have been using, we have to redefine it so that to make it to be good. And besides that, we want it to be conserved quantity. So the conserved quantity is basically, in the case of ADM formulation, is that when we take a slice like this, when we move on, the infinity is more or less fixed, spatial infinity. And all the quantities define the total mass, angular momentum, and linear momentum. They are all the same when you move in that way. Unless you move in a large slice, and then the slice cut down like this, then it's different, okay, in a Penrose diagram. So this is the first thing we should realize, that we are dividing the asymptotic decay according to what the classical physical quantities should be finite and conserved. That's the first thing. And then whether it should be true or not is far away from clear. And then there's, of course, a boundary coordinate that given a cut at infinity, we want to assume we want to define something called boundary mass. There, actually, things are much more complicated than the ADM formulation because we know not much about the now infinity in terms of the ambiguity and all that. But anyway, we'll come back to that later. Okay, now, so let me describe something that most physicists never learned, although we did this 40 years ago at the time when Andy was a postdoc in the Institute for Advanced Study. So, well, I mean, first of all, the mass, if it turns out to be this, and if you write m over r, this is the mass. But of course, you can write it with more general term. Okay. Now, so as Andy mentioned, so Rick, who was my former student, we proved in 1979 the positive mass conjecture. So I describe a little bit about it because it tells you how black hole forms. So we did the following thing. So we look at the slides. Oh, by the way, why I like the initial data formulation is because the initial data formulation could be more non-singular, and it does not touch the singularity that may occur in the future. If you want to know about the event horizon, then we have to know everything in the future in order to decide what event horizon is. Okay. So, well, we know on the other hand, there's a famous theorem due to Penrose and Hawking. Where they prove a existence of a space-like two-dimensional surface, 2D surface, closed surface, which is trapped surface, where it can be derived in terms of the mean curvature of the surface. The two-dimensional surface sitting in space-time, and there are two normal going out. Okay, the normal now is Lorentzian, has two, one outgoing, one incoming. Okay, and the point they want to do is that the mean curvature associated, one of them has to be negative. Okay, so why is that? This corresponding to the light will reflect out from there. Will be absorbed there. Now, the important thing they prove is that this guy would imply existence of a singularity of space-time. Okay, a closed trapped surface implies existence of a singularity in space-time. Now, this is a very funny proof, even now after 50 years. This is done around late 60s, 1970s. So we know this is true, of course, because it's rigorous proof. Everything that we do are rigorous, can be proof. Now this, but on the other hand, is very important because the Schwarzschild solution has an event horizon, and that event horizon creates a trapped surface for you. So the importance of this theorem is that when you take the Schwarzschild or Kerr solution, you can take a small perturbation of that. We know that after you perturb, singularity will still be there, because the existing closed trapped surface cannot be perturbed away. Yeah.
What does trap mean in this context?
Well, we define in terms of mean curvature. That means when light bounces there, they will be absorbed. Okay. So the event horizon has that property, and when we do a perturbation of the trapped surface, if I perturb the whole Schwarzschild solution, after that, the trapped surface is still there. So the spacetime would have singularity. See, at the beginning, both Schwarzschild or Kerr has a singularity. At those days, people thought that the reason singularity exists is because symmetry. Because you create the solution ad hocly by using symmetry, and they thought, well, it's not genetic because you have symmetry. Maybe you can perturb the symmetry a little bit, then the singularity would disappear. So there was a big debate before Penrose and Hawking that singularity may be perturbed away. The Russians think that it can be perturbed away. They even write down some perturbation series to claim that it can be done. So until Penrose and Hawking proved this theorem, that it cannot be perturbed away. So black hole would be stable in that sense. Okay. Now they did not quite prove black hole is stable. They just proved that nearby spacetime must have a singularity. That's all they proved. Now that actually that theorem needs to be improved a lot, because when they prove the singularity exists, they just prove that the space-time is not geodesically complete. But maybe you think geodesic complete is non-complete is fine. But anyway, we know something is wrong. That's all we know. The singularity singularity theorem is not the best form, even after 50 years, because we would like to know, for example, whether singularity would be curvature singularity, like what happens in Schwarzschild or in Kerr, where the singularity has a property that the curvature blows up. But here we know nothing about that. We just know something goes wrong. Okay? You just know something goes wrong, that's all. But anyway, it tells you the closed trap surface is an important thing for you to use for space-time. Okay? If it's there, that means something goes wrong, and we just use that as a so for me and for many of our friends, we define a black hole exists if a closed trap surface exists. Okay? Because this closed trap surface has similar property. The light does not go in the right direction. The light cone structure there. Okay. So this is the first theorem due to Penrose and Hawking, that a closed trap surface implies something goes wrong, and we simply say that in that case it creates singularity, and therefore a black hole exists. So what Rick and I proved is that under what condition? So phi condition that implies closed trap surface exists. Okay. Is it clear? Penrose and Hawking proved that if a closed trap surface exists, then singularity occurs, which we simply declare it to be a black hole in the general sense. And then the question is, under what condition, physical reasonable condition, such a closed trap surface exists? Okay, that's the question we want to address to. So this I used the Rick and I proved in 1982. This paper is still a good paper after many years. I look at it in Communications, Math, Physics. Okay, so let me tell you what the statement is. We proved the following thing. This says if the matter density. Okay, so let me tell you what the matter density is in general relativity. Here. So let's call this 0 and 1, E0, E1, E2, E3. Okay, I take a frame there. 1 is in the future, E0, and we look at the energy density T0, and then T0I square, sum I equal to 1 to 3. Okay, so I look at this one. This is Lorentzian independent of frame. So take the energy tensor, stress tensor, Tij, to measure in this frame. So an observer standing at the initial data, Here's a spatial direction EI, and then the future direction E0. Okay, and look at this quantity. Okay, this I consider to be the matter density for the observer standing there. Okay, so here is a guy sitting on this space-time hypersurface. He measures the matter density he sees using this frame. Now this, of course, we always assume is bigger than equal 0, because we assume the weak energy condition holds, so this is always bigger than equal 0. But what we prove is that this matter density, if it's bigger than a constant, the constant can be written down is in terms of 16 pi square root of pi, I think, but it's a constant that you can write down explicitly. Okay, in terms of r is the radius of a region. Okay, take a region in your space-time, and its radius r. Okay, now you can fix the r if you want. Fix the.
Why doesn't that depend on the path?
Huh?
Why doesn't the radius depend on the path? Why is R well defined?
The r is on the manifold itself, r free in the manifold free. M3 on the slide.
How do you choose the origin? I mean, if that's a curved space-time, how do we decide?
No. Okay. There's something called diameter, which I got maybe I should not say the path, okay? There's something kind of similar diameter of omega. Okay? It's a quantity, it's a little bit more subtle defined. Let me not go into the detail. Okay. So given a region in the initial data, and I compute its diameter. And I said there exists a universal constant, so that whenever this happens, a closed trap surface exists. Okay? So that's the theorem I proved Rick Stern about 60 years ago. I mean, no, 40 years ago. So you can look at it a different way. I fixed the diameter of the region. Then if you keep on adding matter density, then a black hole will form. That's you can put it that way. Okay. This make it to be well. Anyway, it's general theorem. Okay. So this is nice theorem even in geometry, because in geometry you can prove a theorem of this type, but much weaker than this theorem, because this theorem actually allow Kij and Gij. Even if Kij equals 0, this is still a non-trivial theorem. So now this is not the best theorem we would like to prove. We want to prove something more stronger. So gravity has contribution to the whole thing also. So now this statement, when we prove this one, we don't assume it's asymptotic flat. Okay, it's allowed to be more local, this statement. So it's a nice statement. And what we would hope to prove is that given a surface boundary omega, if we can measure the energy of the omega, which should be measurable by something on the boundary omega, which we call quasi-local energy. Quasi-local energy, we would like to say that when it's big enough relative to constant times some r, let's call it capital R now. So what is capital R? This now is measure everything on the boundary now. So suppose I look at far away, and I look at a region in the sky, and I can define something called quasi-local mass, which I will define to you. And if I look at this region, and I can take the following quantity, which are divided by R. R is a closed cycle which is obtained by minimax argument. It's a geodesic on the boundary, which has, so you see, it's a sphere, right, S2. And you can swap out the sphere by family of circles, right? And you among all the swapping, you take the maximum closed curve, and you minimize it among all the swapping. Just like in the case of standard sphere. A standard sphere, circular. So you look at the equator. How do you get the equator? You get family of all circles, swap out the whole thing. Among all this family, you take the largest circle, largest length, the curve with largest length. You minimize it among all this swapping. That gives you the equator. It's a minimax. Okay? So you put it in a more general way. You take loop space of manifold, loop space. You get the energy functional. You take minimax on pi 1 of that. Okay? So the conjecture is this to be true. If the quasi-local mass is bigger than a constant divided by this swap out, a black hole is supposed to form. Okay? Now this I don't know how to prove, but there are many indications that say it should be true. But of course I have not. In here that involves several things you need to do. First of all, you have to prove, you have to define what this means, which I'm going to define. Okay? This is something what we call quasi-local mass. And then after that, then we have to prove this statement why it should be true.
Is there a hope that constant is some number like
Yeah.
pi or something?
Yeah, right. Supposed to be.
It's the thing that you would have to go around black hole.
Yeah. In fact, after we did this one, I realized that Kip Thorne thought about the same thing, but except he doesn't know what the statement means exactly. So we extract some of the statement from his. He said this is a necessary and sufficient condition for a black hole to form. And I don't know what he is talking about, but he is trying to say that if a black hole forms, the inequalities type should hold. So basically, one wants to say that there's an upper bound and lower bound. The upper bound has.
Could that be true? Because this could be in flat space, right? It could be that the matter comes in later.
Well, you have to be careful about what exactly he says, but yeah, I will come back to that later. But anyway, there's the subspecies to be the major criteria for a black hole to form. Okay. Now, of course, when I say black hole, I mean a closed trap surface. So this implies closed trap surface exists. Okay, closed trap. Okay, that's all we can prove. Okay, now let me indicate to you how this can be done, how this was proved. Although this was done 40 years ago, but this argument is still important and useful because we still use it for many purposes. So let me tell you how it works. The argument is very non-trivial, I should say. So suppose I take a slice in space-time. So a slice in space-time. Okay. So this is 3-dimensional slice, M3.
Why is that dimensionally correct?
E greater than 1 over r.
Oh, dimension may not be correct. I have to maybe R square. I forgot. Yeah. But don't worry about it. Okay. Now let me look at the argument, the type argument we are using. I take a slice in a space-time. Now, it's very important we model after some stationary space-time. The argument always comes from there. So let's assume this is actually Minkowski space-time. Okay, trivial Minkowski space-time. Minkowski space-time has a very important thing, namely there's a linear space. So there's a linear space. So let's call V sitting here. Okay. And well, given a slice in a space-time, what I try to find is a phi V without knowing V. So given the three-dimensional slice, I want to find a way to calculate what V looks like. Is it clear? See, I do not know I'm sitting I do not know I'm sitting in the trivial space-time. I just get some data here. So the data, I get G, I get K, right? As I said. So somewhere I reach a point where I'm actually in Minkowski space-time. How do you tell that you actually reach that point? That's the question. Okay. Well, what happens is this. We want to write down V sitting here, and it's automatically a graph. The space-like hypersurface is a graph over V, if it exists at all. Okay. So instead of looking as a function defined on V, I look at F defining on M. So F defines on M. Okay. So I want to find the equation for V. Okay. I want to find the equation of V. So that's a procedure that we want to do. What we do is this. We do an argument of this sort. We take M, I take R here. So now you get a function F. Okay? So I turn the thing upside down. Originally, the M is written as a graph over this linear space. Now I write the linear space as a graph over here. So it has this form. So in the M3 cross R, so in the space M3 cross R, I have a graph defined by a function F. Well, on this I have a metric on M3, and I take the metric on R, so I get a product metric. Okay, so now this surface is defined by F, and in this product metric, I can talk about its mean curvature. Mean curvature of this surface, let's call it sigma. This hypersurface, that's the mean curvature. Okay? Okay. And besides this data, which I got, the data I got is from G so far. But I have still another data, K. Okay. So I take K, which is tensor divided M3. But I have a natural projection from the product into here. Natural projection. I just pull back this tensor in the total space-time. I mean in M cross R. So I can make it to define on M cross R. But just pull back. So in other words, for anything that's vertical, this K will be equal to 0. Okay? So it's extended by linearity. So now what do I have? I have this guy being a surface sitting in a product space as a mean curvature, and this K is now defined everywhere. And I take its trace in space-time, M cross R. Okay. So I look at this equation. The mean curvature in the product equal to the trace of this tensor. Now trace is not that trivial anymore because I pull it back, but the function, the hypersurface is tilting. So the K depends on the normal vector of this surface. So I write down this equation. Okay. Now why are we interested in this equation? This equation turns out to be exactly the equation that V is linear is a maximal space-like hypersurface in Rn, which with asymptotic flat is linear. So in this way, I capture from this data the linear space, if I know how to solve this equation. Okay. So this equation is exactly the equation to calculate the linear space by knowing only G and K. Okay. Okay. Now, so this looks very nice. And now, the important thing is we did a detailed calculation of this quantity. So this hypersurface sigma f satisfies some rather remarkable property. It turns out, if I write, suppose I call T0 to a mu, and Ti0 to be j, okay, mu and j. One is a local energy density, one is a local linear momentum. Okay. It turns out this vector, this mu comma j actually defines a vector. And if I dot product with the normal in here, it comes out to be nice. So put it just the way that I use it, mu minus j, but you can actually write down a dot product. Turns out it's less than equal to the scalar curvature of sigma f. So I take the scalar curvature of this hypersurface. This is a three-dimensional manifold. There's an induced metric from M cross R. Okay, the M is a metric space. It's with Gij defined there. As a hypersurface there, there's an induced metric. Okay, and then plus some other quantities, which let me not go into detail there. Okay, it's set of inequality this type, which we calculate in terms of all this data that we have. So the important thing is that
The difference depends on K?
depends on K. Yeah. Depends how it tilts on K. Okay, this can be calculated, and this lengthy calculation, but it works out okay. And what's the whole point of here? This inequality allows me to deform conformally of the metric on sigma f. Okay, I take the hypersurface here, and I can deform its metric conformally, so that after deformation, after deformation, so let's put it to be psi to the power 4. Okay, I deform the surface by psi to the power 4, so that the scalar curvature of this deformed metric is positive, is not negative. Okay. Within the conformal class, this induced metric, I can deform it so that the new deformed metric has positive scalar curvature. Okay, but actually it's more than that. But let's just say we know this fact.
You have to do something singular to infinity?
Well, no. I mean, the psi will be asymptotic 1 in a strong manner. Okay. So the important thing how we prove the positive mass conjecture is that actually psi will be vanishing, will be equal to 1 up to high order. The total mass is not changed in this deformation. Okay. There are two parts which we use for prove the positive mass conjecture. One is to make sure that sigma f has the same total mass as the original guy, and then here we also prove the total mass is not changed. Okay. So what is the procedure? The procedure is to go from M, which we want to deal with. This is an original metric. I go to another space, namely this guy. Okay, and then I go to another space by conformal deforming it, and then at n I make the scalar curvature to non-negative. Now, what's the procedure we are doing? Originally, when I say mu minus j is non-negative, here is a local energy condition, weak energy condition. That condition is now transformed to this one to equal 0, because now I make this one to a non-negative. In other words, I produce a new metric where it's equal 0, basically. And this one sets a local energy condition, and the total mass of G tilde is the same as total mass of G.
Do you have to solve a differential equation to show this?
Yeah. Everywhere we need to solve a differential equation. Okay, I'm coming back to that, but let's say that this is a procedure we've solved the positive mass conjecture. Okay, so given a metric, we solve this equation, and we conformally deform it. We solve two sets of equations, and not just one. Okay, the first set is to prove this exists. The second set is to prove this can be deformed. Okay, so there are two steps here. They are non-trivial steps, both of them. Okay, actually, the procedure works even if the local energy condition is not true. It still works. Now, so how does black hole come in? So far, it doesn't seem that black hole will come in, but it actually comes in now. When we try to solve this equation, by the way, we call this equation Zhang's equation, because he was interested in it, but he does not know how to solve any of this equation. He gave up because he didn't know. He thinks it cannot be solved. Indeed, this equation cannot be solved globally. And the obstruction for the existence is interesting. That's why I'm trying to tell you. Namely, the mean curvature of sigma f in M cross R, this equation is equal to trace k. Okay, that's the equation we try to solve. This equation cannot be solved always. Okay, so well, we're going ahead to do it. In any case,
Which equation can't be?
this is the same equation I wrote down here. This equation that I wrote down. I want to solve this equation. This equation cannot be solved. This equation is a put in this way. This equation is an equation, second order elliptic equation, can be written this way. It's second order in F. Okay. And the k comes in and all that. Okay. Let me not write in the detail. It's like mean curvature equation. Second order elliptic equation. So it cannot be solved. It's easy to produce counterexample, so Zhang actually gave up. So what we do is that we want to solve it no matter what. So what we do is that we do a perturbation. So I put the epsilon there in front of f. Okay. So we prove that this can always be solved for epsilon is positive. Can be solved. For epsilon strictly positive. Okay. This is a non-trivial fact that you can solve it all the time. This involves a lot of estimate on minimal hypersurface and all that in this product manifold. So the first thing is that we know that it can be solved. The reason that it can be solved cannot be solved here without putting epsilon is because we cannot control the height of f. So the maximum of the height needs to be controlled. Okay? And if it can be controlled, then this can be solved. Epsilon can go to 0. So what happens is that the equation can be solved. You call epsilon here. It depends on epsilon. If this is uniformly bounded, independent of epsilon, this implies epsilon can go to 0 and can be solved. Okay? Because the uniform bound, I take epsilon go to 0, I can solve everything. This can be proof, not trivial. Okay?
Didn't you say a second ago there were counterexamples?
Yeah. So therefore, it's not true. And I'm going to tell you how it's not true. Why these are interesting with black hole. This is exactly the point.
Are you putting a boundary condition in
The infinity boundary condition infinity is f go to 0. At infinity, always. Okay. So in fact, you don't have to go to infinity. It's just a big region and fix some boundary condition. That's all. Okay. Now, why is it not solvable? And this is exactly how the black hole comes in. That's why I want to talk about it here. We do the following thing. We solve f epsilon. F epsilon can always be solved. It could look like this. Okay, could look like this. And you go to 0 rapidly and infinity. And spatial infinity, so we solve it. All right? Now we prove that it's true, always true. And we also prove the following thing. On this is on the product manifold M cross R. The whole thing happens on M cross R. We prove the following thing. You take any region here, so you take any box, O cross interval, a big compact set here, cross interval. The graph converges. Converges in this neighborhood. Okay? I take any compact box in this product manifold, the whole graph always converges when epsilon goes to 0. Okay? So what goes wrong? Well, the whole thing converges. The first important thing we prove is that even though it may diverge somewhere, we prove that it always converges at infinity. In other words, we find a region at infinity where no matter how epsilon moves, it must sit inside here, inside this region. Okay? That's the first thing we prove. So it's sandwiched in between a region which f epsilon cannot move out. Okay? So what it means is that f epsilon always converges in some region, namely near infinity. Okay? Okay, so what can go wrong? What can go wrong is that on each compact set converges, it may go wrong is that you start to go to infinity, like this. The graph itself is a very nice, beautiful graph, except as a function, it does not converge. The function blows up. Okay? So the picture looks like that when epsilon goes 0. So everywhere it converges near infinity, but in compact set, some part will go to infinity. Okay? Now, where does it go to infinity? We prove that it blows up at the region where is a parent horizon. So there are trapped surface. Then whenever it blows up exactly on the trapped surface, which is kind of understandable. You look at this equation, this, when it's near the infinity, the normal at the beginning was 10 this line, now eventually it becomes horizontal. And this line is a straight line. So the mean curvature of this one in the M cross R becomes a mean curvature of the surface in M3, in the free space. It turns vertical. Okay? And this becomes the trace what you define in the trap surface that appear. Okay? So one is called future trap, So the psi comes in, one is path trap. Okay. So the F epsilon eventually converge in this way to a trap surface, either in a future trap or past trap. Future trap means you go to infinity. Well, of course, the whole thing has symmetry in time, so you have to fix which orientation you want. But it could be future and past. Okay.
Is the differential equation getting singular there?
Yeah. No, the equation is not singular. The whole thing is very non-singular. And the surface is actually smooth as you want. And we can prove this surface actually is exponentially converging down to the tube. So in other words, this guy is actually smooth. And it's a smooth surface. You cross it out. It's a very smooth, beautiful tube. And if you look at this surface from the point of view of the tube, it's a nice, beautiful graph over the tube, going down the smoothly, going down the CO smoothly. Okay. So that's the picture. How a picture looks like. Is it clear? So what does all this mean? This means if I can solve this equation, well, then it has a globally defined hypersurface. So if the equation can be solved, right? Then I get a hypersurface, everywhere defined, non-singular. And the total mass and many things are the same as original one, as m, total mass for m. And then many other things are the same. And now the good thing is that the scalar curvature, or sigma f, is non-negative. So this basically reduces the problem of non-time symmetric case to a time symmetric case, so to speak. So you can look at it as a time symmetric case, namely this corresponding to a G with 0, k equals 0. Okay? Because this means the energy condition holds. So this procedure allows us to study a problem which is non-time symmetric, which means k is not equal to 0, to the case where k equals 0, which is time symmetric. Okay, so it's a reduction for a non-time symmetric situation to a time symmetric situation. Okay. Now, on the other hand, if it cannot be solved, trap surface exists. That's what I just showed. I mean, F epsilon will converge. It will converge to something. If the closed trap surface does not exist, the whole thing converges. So it must exist. Not only exists, it exists in a very nice way. We know that it's smooth, and we can also estimate the diameter of this surface. That takes some work, but we know how big this spheroid is, in fact. And
in terms of what?
Well, in terms of the matter density and all that, okay. The bigger the matter density, the smaller the hole is. That's what we can prove. Okay. So when I write down the inequality, this is actually the bigger the density, the smaller the hole will be.
But couldn't we have no matter and still have a trap surface?
Well, that's a thing. I mean, so this is a black hole created by matter. And the conjecture I want to make is quasilocal mass. It may not have matter. That's a different thing. I wrote a paper later. That's about 25 years later. I wrote a paper which says about no matter. You can still create a black hole. Okay? But I want to mention this because this gives you a procedure to create a apparent horizon. And in fact, you can prove every apparent horizon can be obtained in this way. Why is that true? You see, we have a family of surfaces, F epsilon. F epsilon. Now, epsilon could go to 0 in many different forms. A sequence goes to 0. What we can prove is that when epsilon goes to 0, you must converge to something like that. But you have different sequence, you may converge to a different configuration. Is it clear? Mathematics allow you to do it. Your sequence and your subsequence of different form, they can converge to different ferrule. So you can prove that any apparent horizon in your space-time can be obtained in this procedure. So you don't miss out anything. Any apparent horizon can be obtained in this way. So all the black holes can be found in this way. So now, what's the point of this? Suppose we have this ferrule with a singularity like this. The manifold itself has what property? It's either asymptotic flat, which is true here, because the region near infinity is just as before, or it becomes a tilt. It becomes a tilt. And this kind of tilt is very well understood because it's exponential decay to a cylindrical surface. And it's so well behaved, I can close it up. I can use a metric to close it up so that it becomes a space-time. And this becomes a free manifold. A free manifold, maybe call it hat, with scalar curvature, non-negative. Okay. And the total energy is the same as before, so this everything is good. Now, I should say that free manifold topology of scalar curvature positive is well understood. After a lot of work, the first work was due to Richard and myself. We know what they are. Free manifold positive scalar curvature has to be sphere, of course, or sphere chosen by some finite group. Okay, so length space or some, finite group acting with no fixed point. They are classified. We know them all. And there could be S2 cross S1. You take S2, circle, that's it. Okay? And of course, you can also cosin S2 cross S1 by some finite group also, if you want. So these are the basic building block of three-dimensional manifold positive scalar curvature. And you can also take the connect sum among them. Okay? So what's connect sum mean? A free manifold connect sum is a free manifold. You take a tube joining them together. Okay, that's called connect sum. Okay? So for example, S2 cross S1 connect sum. S2 cross S1 is like a donut like this, and another S2 cross S1 you join a tube. Okay? This produces a three-dimensional manifold with positive scalar curvature. And we know we can prove all of them looks like this. All three-dimensional manifold positive scalar curvature looks like that. Okay. So this produces a important consequence on space-time, which is asymptotic flat. That means outside a black hole, we know completely the topology of this three-dimensional manifold. It is always like this ferrule by puncture some points. Okay, that's basically what it is. And take out some black hole. Okay, like this. This black hole is always S2, by the way, topologically. These are always S2. So topology of three-dimensional manifold, this is a non-trivial theorem because it involves Poincare conjecture. The statement says that any three-dimensional manifold, any universe which is asymptotic flat, outside a black hole, it must have this form. No more. Okay. This ferrule puncture a finite number of points. Is it clear?
The puncture could be at infinity too, right?
Yeah, puncture, a close-up infinity by point. Okay, so this tells you the topology of three-dimensional manifold must have this form, no more. That's of course assuming we satisfy the local energy condition. Okay. Now
So what are you saying? If we take a genus 2 surface times S1, there's no
cannot.
solution of the constraint equation? Is that what you're saying?
Well, you will have a black hole inside. The topology could be sucked inside the black hole. Then right now I'm taking the things outside the black hole. Okay?
So any such thing would be have a horizon.
We always have a horizon. Yeah. Always have a horizon. But there are many free manifolds besides this you should know. I mean the hyperbolic space form and all this one we could not support those things. What it means is.
And this, of course, is all having mu minus j positive, right?
Yeah, mu minus j. We are so mu minus j positive. You are so mu minus j bigger than equal to minus 1, you have a corresponding theorem, but it's not as clean as what I wrote down. Okay? It's a asymptotic anti-de Sitter space and all that. But anyway, now, after many years, I look at this problem again. We try to prove the positive mass conjecture. We achieve it, then we are very happy after a lot of work. So we just say that we accomplish it. But if you look at it more carefully, there's no reason we don't consider things inside. F epsilon could still converge within the hole inside. And this hole, the F epsilon, it blows up along here, but in the inside it could still go. It could still converge. If everything goes well, this would tell you more general than this statement. If this statement only works for space-time, which is outside the black hole. But if I look at the limit of F epsilon, I will be able to tell what the topology and what the geometry inside the black hole would look like. This, after numerical calculation, looks not bad, but we don't have a theorem yet because, we prove theorem is really very slow compared with physicists, just talks. we need to make sure that it's right. So it takes a lot of work to do.
But so
I
you're
just
saying
make fun of you, don't worry.
So, but you're saying that you might be able to rule out some topologies?
Possible. I have to see what the limit looks like. If the limit exists, and then I can say something about it. Okay. But the picture is all here. Okay. The F epsilon converges inside. Yeah, at least it pokes the interior of the black hole. This shows that. Okay. And actually, some numerical calculation shows very, very interesting picture of how these things goes. I mean, it grows up here, and this inside goes like this, and the way that they kind of join together is actually oscillate a lot. So I'm not sure of the picture yet. Okay, the way that they join from exterior black hole to interior black hole, the join is a highly oscillating behavior, and maybe a lot of information was trapped inside that oscillating behavior. Okay, so this is about which I think is interesting because I think this tells you something about black hole, and I think understanding this solution is still a very interesting thing to do. You can do this one in high dimension also. You can study black hole in high dimension in this topology, but at the end it reduces down to study metric positive scalar curvature, which fortunately we know everything now. Assuming point conjecture is proven, then all these are known. But 4 dimension we know something, but we don't know that much for 4 dimensions. Okay, but it still tells you something. So maybe we can take a 5-minute break and then we can talk about.
Sure.
Okay, so I talk about quasilocal mass. Then I need the screen back. Yeah?
Screen back.
Yeah. How do you do that? Let me get, yeah.
Just a technical question. How does the limit manifold
So, by the way, the high dimension version of this theorem can be done, but it's much more tricky. The argument is dependent on dimension reduction, which is kind of interesting. So we go to high dimension space and we take some slice in a suitable way, and we keep on going down to lower dimension. I wonder whether that actually means something to general relativity, in fact. Anyway, so now let's come back to quasi-local mass. As I told you, I like to get rid of the energy density. We want to talk about quasi-local mass. When there's no density, we still want to prove the same thing. So we know, so I want to define what quasi-local mass means now. Well, first of all, this is Noether who proposed that if space-time, if it's time-like Killing field and all that, you can use the Lagrangian to define current associated Killing field. Everybody here knows it, I assume. And so the actual statement is that if you get a diffeomorphism on the space and you leave invariant the Lagrangian, then you can write down the Euler-Lagrange equation by differentiate the action and get that. Okay, so that's how Noether's theorem can be formulated. And now I'm making the simplest asymptotic, where, as I mentioned, Gij equals delta Ij plus 1 over R and all that. And as I said, it's not clear this is the best asymptotic condition you want to impose. Because I believe there are many more space-time which is asymptotic flat in a weaker sense, and yet most of the theorem that we are talking is not true. I mean, because we do need to make sure that things converges. It may not converge anymore. But the concept of quasi-local mass will be good enough to deal with that, even if it doesn't converge. There's something good about it. So the reason why you need convergence is partially because this is the definition. It's actually written by Einstein himself. Write down the right-hand side on the mass, and it depends on the choice of coordinate near infinity, and you want to make sure it converges. If the metric converges dies down in the way that we said, we can define this with no problem. So it converges. But angular momentum becomes a tricky thing because it's much easier to diverge. So the boundary size coordinate near infinity, now infinity. You were a student of of Andy's, you certainly know much better than me about this boundary coordinate. And so you can write down the boundary size energy momentum vector. And so you can do it, assuming you have the nice coordinate like that. So all this we know that total energy cannot be integrated along a hypersurface. So it depends on how do we define it in the right way. So now quasi-local mass is the mass or total energy momentum 4 vector, which is assigned to any space-like sphere bounding a compact portion of a space-like hypersurface. So we attempt to do it now. So without density, but on the other hand, we want to assign a 4 vector to a compact surface. So this was actually, I was interested in this because Roger Penrose was in Institute for Advanced Study, and this was in 1979, and he considered this one of the most challenging problems. So we were interested in working on it. So we hope that I was interested in it partially because most of the dynamical equation in general relativity depends on what we call the energy method, which follows in the standard arguments in hyperbolic differential system. But those energy methods are not intrinsic. Energy is defined in terms of coordinate system, in terms of all kind of gauge, which is not natural. So I'm hoping that the quasi-local mass can be used to replace the energy method, which is more intrinsic and more interesting. So anyway, so let's look at the following approach, which is pretty well known to many people. And so this is Lagrangian, and in order to keep the boundary, so you have the boundary term 1 over 8 pi times the integral of the mean curvature on the boundary. This was I don't know who was first one to use it, probably Hawking and Gibbons. I'm not so sure. At least in the formulation of Euclidean gravity, they use this. Okay, so this, the boundary term, in order to keep the right variation equation, you fix the matter and the matter field on the boundary. So whether you want to do it or not is a different question, but you want to do it, you will fix that. You will have the boundary term. And so suppose we need a background in order to make sure that everything is trivial in Euclidean, in the trivial spacetime, namely Minkowski spacetime. So we want to subtract out the background by doing that. So in the flat spacetime, if you use the background to be flat spacetime, this term is 0, nothing there, so it's 0. But the mean curvature is not 0 in the flat spacetime, so we have that. Okay, so this is the proposed action that we need to use. And now, in general relativity, almost everything, at least in the classical one, everything is related to gauge choice. You don't have the right gauge choice, everything goes wrong. So the whole thing here is the question of how to choose the right gauge. So first of all, we fix the timeline vector, and we have a gradient vector field associated to it. And the gradient vector field is supposed to be trajectory where the observer is observing the space. So you write some part of it to be normal of the space, and some part of it is tangential to the hypersurface, codimension 1 hypersurface. So n is called the Labs function, n mu is a Sieve vector. That's a well-known in GR that you do that for 3-dimensional slice. And then in this notation, it turns out you can write down the action in this form. So n is Labs function, dt is a t that you choose. And now p is actually my k that I wrote down earlier. P is a second fundamental form, and p squared is a trace. And so you rewrite the action in that form. Okay? And now K2 is the mean curvature of the 2-dimensional surface for ST. So you take a domain in space-time where T is swept out some surface, 3-dimensional surface, and you write down action in that way. Okay? So with this action, you can do the conjugate momentum, canonical momentum is K mu nu and K conjugate 2. And you can rewrite this action to be that form, and then you find a Hamiltonian constraint. I have this form, and this is the momentum constraint. Both of them can be written down. And the equation of motion is satisfied if both of them are 0. And so that's the equation. When the equation of motion is satisfied, then both of them are equal to 0. That's a constraint equation that you probably learned already. So what do we do now? If R nu is a space-side unit normal to the surface, 2-dimensional surface, and sitting in a 3-dimensional slice, sigma t. So ST is sitting in sigma t, 2-dimensional surface. We take the unit normal there. And if we do that, so basically this is the picture that you see. Sigma t is a 3-dimensional surface, and ST is the boundary, and R nu is tangential to sigma t, and T nu is the time vector. Okay, n nu is a normal vector to sigma t. There are two kinds of normal. One is normal of sigma t in space-time. R nu is a normal vector of the 2-dimensional surface in the 3-dimensional manifold. Okay, so that's the picture. Then you can derive by Hamiltonian mechanics to you get h equal to this, and this is nice. But it depends on Labs function and depends on C function. Now, on the other hand, the first quantity is fine because on cell, when the equation of motion is satisfied, this guy equals 0, this guy equals 0. Okay. So the only thing left when you are doing on the equation of motion, when the space-time satisfies the equation of motion, the only thing left is this term. Okay. So that's how you derive the energy. Okay. Of course, the problem here is that what is n and when is n mu? These are two gauge terms that is there. Okay, that's how the 3-dimensional slice moving in space-time. There's a Labs and also there's a gauge. See. So what we do is this is what all these people who does quasi-local mass knows this term. The problem is how to choose n and n mu. Both Brown and Young and Hawking and Horowitz do the simple thing, just choose n equal to 1 and n mu equal to 0. And this is certainly not canonical. Given a two-dimensional surface, when you choose this, it depends on the three-dimensional manifold. It bounds, and it depends on many other things. So more importantly, this definition does not work to be positive in a time-symmetric case, except in a time-symmetric case. And this was proved. I talked with my friends in Hong Kong, and they proved that in the case of p equals 0, that's actually positive. And this is already a very non-trivial argument. It depends on the prove the positive mass conjecture I just mentioned. Right? Okay. To prove this term is positive is a non-trivial statement. And in order to make it to be gauge independent, Marisa Liu and I pose a condition which is gauge independent, namely this term, and this is gauge independent, and also we proved that it's positive. So that's pretty good. We were proud of it at one point. But then it turns out to be too positive. So for surfaces in free space, in a trivial Minkowski space-time, this guy could be strictly positive, non-vanishing. So we don't really like it, but the proof is non-trivial, and we still use this kind of proof later. This used a lot of arguments, actually, both the argument by Rickson and myself, and also Ed Witten's argument using the Spinor. So both arguments are used. At the beginning, many people say that this proof is better and that proof is better. Actually, both proofs are important, and both proofs should be combined for all these arguments. Okay. So in Ed Witten's argument, there's a question of Dirac spinor, but we have to allow the spinor to jump because we are doing a surface inside and something outside. The positivity eventually was reduced to the positive, the total mass in a non-compact space-time. So we have to put two non-compact space joining with something in the compact side together. So there's a jump on the boundaries. That's why there's a discontinuity we have to deal with. But anyway, it works out, and positivity is okay. But now this doesn't, as I said, it depends on, it's too positive. It's not good enough. So finally, after many years, and Mudao Wang, about 10 years ago, we start to get the right thing, I think. So I'm trying now to describe to you how this works. Given two-dimensional surface, which we want to prescribe a quasi-local mass to it, and we assume the mean curvature to be positive, the spaceline, the mean curvature vector is spaceline. This is needed, otherwise the geometry is very complicated, and it's not clear that it can be defined in that case. And we isometrically embed S into the Minkowski spacetime as a reference frame. And then the important thing, observation that we know, which is very important, is a choice of gauge, as I mentioned before, is this equality is a whole. What's this equality? So let's look at the picture. The picture is this. I embed the surface into R3, as by isometric embedding. Okay, there's a reference, isometric embedding. So I take an observer called W nu. So W nu is a constant speed unit vector. It doesn't need to be unit, but a unit. But anyway, it's a constant traveling there. So this guy was observing this embedded surface, and here's the mean curvature x0. Now I want to look at this quantity. Well, first of all, I write W nu to be in this one. There's a Labs function, there's mu there, and I want this one to hold. So the mean curvature dot with W0 is a intuitive thing. It means that if you let light coming from W nu direction, you look at how you expand or contract when you bounce at the surface. This is this quantity. This quantity measures when light comes into surface, how you contract or expand. And I demand it to be the same as this quantity where I define W bar in that way. Okay, so this tells me how to construct a gauge.
What's n bar then?
N bar is a vector sitting in there. That's how we choose the thing. Okay, n bar is defined so that these two equation holds. Okay. Okay. So in this way, I get a vector field, not a vector. W nu. See, on here is the constant observer. Is observer traveling in the reference frame in a constant manner. So that's canonical chosen observer. And from this observer, I find an observer here along the body, W nu. Okay, it's a vector field now, normal vector field along the thing. And it's satisfies this condition. Okay, which means that the contraction or expansion of the light is the same. So this is important for us, and this tells us how to choose our thing now. So we found there exists a canonical gauge so that we can compute this one now, because we choose that. Now there's another, so we define this thing in that way because I found what W bar is, and I plug in here now. See, once I know what n and n mu is, I know how to let this quantity now. Now, but there's a problem here because as it is, it depends on the choice of the embedding. You know, I isometric embed my surface into R3, 1, and there potentially huge amount, infinite dimensional embedding of the surface in the R3, 1. So we need to make a choice. Now, in order to make a choice, we better understand this thing first, because this thing is kind of complicated. It looks funny to you at the beginning. You know, I mean, so this is surface in Minkowski spacetime. This is something that we come up in a PHYS calculation. Is something that we cannot ignore. But it turns out, after reading Gibbons' paper, we found Gibbons did something. He's just interested in Minkowski spacetime for somewhat different reasons. But he made a very good observation. Very few people seem to know. Is that this quantity turns out is equal to the total mean curvature if I project the surface S onto the orthogonal complement W mu. You remember, W mu is a constant observer. So, see, W nu is an observer traveling at constant speed. I take the orthogonal complement of it, and I project this surface into this orthogonal complement. And it turns out this becomes a very nice thing. This whole thing is just a mean curvature of the projection, the total mean curvature. So very clean. At the beginning, it was rather complicated. After you project, it becomes total mean curvature. So this becomes very good because now we understand what to do, because it's very nice geometrically thing. This also indicates why this quantity is good. Okay, so that's what the picture is. I project the surface into R3, which is orthogonal to W nu, and I took the total mean curvature. Now, so what we have is the thing that we define. W is this constant vector. We got this quantity. Okay, this one is from on the space-time. This one is in Minkowski space-time, the relative version. Okay, and as I said, we understand what this value is. So the very important thing is that we prove EW is non-negative. Now this takes a non-trivial work to prove. There's the whole positive energy theorem and many details has to come in. It takes a really long discussion to prove this one. So it's very important we know EW is actually non-negative. Okay, if it's not, if it doesn't have a lower bound, I cannot take infimum. It's because there's a lower bound I can take infimum. Okay, so I define this to be my energy, okay, after minimizing, okay. So this is my definition, and this is automatically non-negative. Now, of course, you said, well, you minimize many things, but it turns out it's not so bad because we can actually calculate this equation, EW. So W is I can isometric with a surface into that. When I'm minimizing it, there's a critical equation, Euler-Lagrange equation. This equation is a fourth order elliptic equation, turns out, nonlinear though. So what is this equation? Looks complicated, but it's actually not that bad. Tau is a height function over some free space. Tau is a function that we want to solve. And you divide sin theta by this equation. Okay? So tau is something you want to solve, and you plug that in, and you can solve it. It's a fourth order equation. And this you can prove that this equation is actually not bad, except maybe some singular points. It is continuous, but on the other hand, you may not be smooth. But everything is controlled, so don't need to worry too much about it. So you can actually compute this solution of this equation, given a h and the data on the two-dimensional surface. This can be computable. By using a computer, you can do it. And also, this guy has a unique solution if the surface is close enough to sphere. So, for example, if the surface is asymptotically to infinity, this solution is unique. You can write it down. And you can write down the solution perturbatively, actually. So this is a very good thing that you can do. And so we proved that it's non-negative among all isometric embeddings. And this uses, as I said, actually quite a lot of different technology to achieve it. I mean, it's a really accumulation of about 20 some years work to do this, starting from the proof that I did with Rick Sher. Okay, all these are used actually. So what do? They have a very good property. It's Lorentzian invariant. It's built in there. It's trivial for surface in Minkowski spacetime, and future timeline for surfaces in spacetime, which satisfies the local energy condition. And when it's a spherical symmetric spacetime, so they are folded by orbits of SU2, and suppose you divide out by associating to its area to 4 pi r squared. So standard way to associate out to the orbit. The mean curvature vector of the orbit can be computed. It looks like that. And after that, then it turns out the quasi-local mass of the orbit sphere, as I defined earlier, is equal to this. So the mass of the orbit is actually r times 1 minus squared r. And this is actually interesting. We prove this always positive. It's not a priori clear that it's positive. In fact, it was only proof. In some cases, it was positive. I mean, Misner and Sharp define a little bit different. You see, you get gradient r squared here, but
this is only for spherical symmetry.
This is only for spherical symmetry. We're comparing our mass with the spherical symmetric metric. Okay, so see, we don't have square here, and
you can't just compute that.
Huh?
You can't just compute gradient.
Well, we cannot compute. No. Well, I mean, the sphere could be wobbling around. It's an orbit. I mean, the sphere itself is fine, but then it moves around the way. Okay. So the mass actually is interesting. The mass that we define, see what Mr. and Sharp defined is a Hawking mass actually. It's same as Hawking mass. I mean, Hawking probably learned from them because Hawking defined it later. So Hawking learned the Hawking mass from them. But Hawking mass is not positive in general. And so it turns out we can compute. This mass is related to our mass. This is the Mr. Sharp mass, and this is our mass, capital M. Okay, this is the relation set like that. And this has a remarkable fact. It says small m is actually between capital M and m over 2. Capital M is our mass, and small m is the Hawking mass. Now, even the Hawking mass's positivity actually was non-trivial. Even in 1995, Christodoulou can only prove that the Hawking mass is positive under some assumptions. So on the other hand, our mass actually is always positive. We proved that. So it implies that it's true in general, even the Hawking mass. Now, but on the other hand, it's interesting because they are not equal. You would believe that. I mean, any mass should be equal to the spherical symmetric one, but they are not quite. but they're true only up to 2. Up to 2. And in fact, at the event horizon for Schwarzschild is equal to 2m, and at space-solar infinity, they're equal. So on the space-slow direction, it decreased somewhat, but not badly because only up to order 2. So the only thing we can say is equivalent. Equivalent in the sense up to a constant, universal constant. They're the same. In the case of spherical symmetric case, and so Hawking mass on the other hand, is monotonic increasing along some inverse mean curvature flow, and so this is useful for many purposes. So what it shows in particular is our mass is also monotonic in some sense, but not exactly. It's only up to 2. Now, it's very important to see what happens in the timeline and now direction. We suppose that it will decay, and we can prove it in some cases, but what will happen in general is actually very important for understanding dynamics of the Einstein equation. This mass turns out to be interesting. My former student, Robert Barnett, who's a really very good mathematician, he defined a different mass when Pij equals 0. He defined it by minimizing ADM mass among all asymptotic flat extents of the data, which does not contain a apparent horizon, which extend the origin data. This mass is defined in a little bit different way and is always positive. So we compare his data with ours, and I will tell you how it comes out a little bit later. First of all, this mass recover the ADM mass and recover the boundary mass, and the question is, how do we compare these masses together? And this turns out to be quite interesting. First of all, I'm cheating a little bit because we do not quite define 4 vector. You remember, 4 vector is the mass and also linear momentum. They define 4 vector. Now this is because we are assuming things are near asymptotic infinity. It turns out if you take C as a sphere converges to infinity, then in fact the function, see, what we define is only a function on the light cone of the Minkowski spacetime. And this function may not be linear, so that the function need not be defined as a 4 vector dot product. This is true, on the other hand, if the sphere is going to infinity, on infinity. And this actually, I think, is a good sign, which means that when near infinity, things are linear and produce ADM 4 vector. When it is in the near strong field, it's not linear. It indicates the nonlinear phenomena of strong field, and I think that's very reasonable. And well, in any case, if the space side go to 4 vector, go to now infinity, then this becomes the boundary Sachs 4 vector. So the function associated co-survey in general is nonlinear, but you can solve it. And now, for many important cases, we actually did the calculation, which I don't want to go through the detail. Let's see. This defines ADM angular momentum. Let me not go into this boundary mass. Okay, I don't really have time, but this is much more developed using here, especially when the sphere, spatial 2-dimensional sphere going down to a point, this mass is going down. So when the sphere goes down to a point, the limit of that is the RQ term. This is R. The RQ term gives you the density, matter density. If matter density is not 0, you take the energy of this thing, quasilocal mass. It will be RQ because the sphere is the ball radius RQ. Density will come out exactly. But if the matter density is 0, then the second term will be R5. And this constant here would be the Bell-Robertson tensor at this point. Okay, and so when the sphere goes down 0, it either captures the matter density or capture the Bell-Robinson tensor, which I think is reasonable because the Bell-Robinson tensor kind of describes some gravity content there at that point. Now, the difference between baronic mass and our mass is that the baronic mass that in the time-symmetric case, in the R5th term, it seems to go down to 0. There's nothing there. But I think so I think this one is more natural than the baronic mass as a result. But anyway, there are a lot more to be discussed and relating to gravitational radiation and all that, but I don't have time to talk about it today. So I'll stop here.